Hi, welcome to our thermoelectric energy project based on a heat waste recovery turbocharger. Hi, my name is Jason, and our thermoelectric system is quite similar to those used in Formula One and higher-end vehicles manufactured by Mercedes and Porsche. The turbocharger system effectively acts like a turbine collecting the energy from fluids, in this case heat waste gases. On the opposite side of the turbine, or the hot side, is the compressor, or the cold side, which feeds air into the internal combustion engine. Our system is housed in between both sections, turning that rotational power into electricity through magnets and copper coils, essentially acting like an electric motor or generator. The energy generated is transformed to lithium batteries to later be used on by a separate electric motor that is connected to the drivetrain.
This system is based on a 2004 Mazda Speed MX-5 Miata, which already comes with a turbocharged engine. We're using a turbo that produces up to 8.5 psi of boost. It's paired with a 16.5 kilowatt-hour lithium-ion battery that gives an estimated range of 80 miles. The generator chosen outputs 14 kilowatts and runs at 90% efficiency. And since this is designed for Miami, we factored in the warm, humid climate, electricity at 15 cents per kilowatt hour, and gas at $3 a gallon. Overall, the system is expected to cost less than $4,000.
When it comes to the values produced by a thermoelectric system, we were in the ballpark with the thermal efficiency not being so far off at 64.7%. When it came to the power range of our generator, it closely matched and surpassed our expectations at 13.5 kilowatt hours to 17.9 kilowatt hours. From the components, we selected a 120 kilowatt electric motor to drive the car, paired with a 16.5 kilowatt hour battery, should give the driver an extra range of 80 to 90 miles at a continuous driving time of 1.5 to 2 hours to charge that battery fully. An unexpected outcome from our system came with the miles per gallon, providing an extra 31% in miles per gallon compared to the 20 miles per gallon city the Miata came with the factory.
Moving on to the next slide, we're now focusing on cost analysis. On the right side, there's a table outlining the various components required for the thermoelectric turbocharger system, along with the rough costs. For example, the turbocharger itself is estimated at around $1,195. The total cost range for the full system falls between $19,620 and $22,840. While the regenerative braking hybrid may seem like a more affordable option initially, projections show that the thermoelectric turbocharger becomes the more cost-effective solution in the long term. As mentioned in the second bullet point, there's an added benefit, not previously highlighted. Charging the battery using waste heat can save fuel costs by reducing the need for gasoline, with an average saving of about 13 per full charge. This table summarizes all the specifications such as efficiency, charging times, battery mileage, fuel economy, and long-term profit. It's clear that each system has its strengths, but when considering long-term value, the thermoelectric system stands out.
Alright, hello, my name is Sebastian, and for this slide I'm going to talk about the consumer outlook, which basically has to do with the general state of a consumer perspective and some of the benefits, where overall the thermoelectric system is going to be more efficient and have a benefit in manufacturing, where it's actually going to be cheaper to manufacture compared to other cars, while having a low cost to charge a battery, which really is only going to be $2.47 for the average charging rate. The battery is even going to be able to be charged while driving, since it is being regenerated, where it can be charged in 1.5 to almost 2 hours worth of driving, which actually is going to be less time than a car with a regenerative braking system. And with all this in mind, overall it's going to allow the consumer to have a more practical vehicle, especially for daily use, because of the fuel and battery efficiency and the low charging costs, and even also a small upper hand in performance as well. When looking as far as the industry is going to be concerned, today's market has become heavily demanding in new electric cars, while governments are trying to push for more electrification in future cars, meaning that the goal is to manufacture more electric cars and get people to buy more electric or hybrid cars. And this is going to cause a larger demand for new designs to allow newer cars to be efficient and reliable as possible. And this is where we feel the thermoelectric system will fill that need, and where it can be implemented into newer cars while having that efficiency/reliability, low manufacturing costs, as mentioned before in the previous slide, and even performance, which in time can be improved upon and perfected to be more and more competitive in the automotive market.
The system shows strong potential. There are four main areas we're working to improve. First is efficiency. We're currently at 64.7%, and we're aiming for 70% by refining the turbine blade design. Second is cost. The current setup costs over $4,000, but this can drop with mass production and cheaper components. Third, we're tackling thermal management by improving insulation, using better heat exchangers, and adding active cooling. Finally, for integration, we're focused on making the system more compact to fit easier into existing engine bays.
Thank you for watching.